All right, and we are on our last problem for this exam, so don't be phased. So fill out all sections of the phase diagram. So we know that this is going to be BCC plus liquid, BCC plus this phase, liquid plus this phase in here, FCC plus this phase, BCC plus this phase here, this plus this right here, this plus this right here, this plus liquid right here, MU plus BCC, and then liquid plus BCC. And you can write those all out. Excellent. We need congruent melting points. Here's one. Here's basically like another one here. Here's one here, and then here's one there. Those are your congruent melting points. What about some other invariant points? We know that this is going to be eutectic. This is BCC to a two-phase region, so this is a eutectoid. Also here we're going from a single phase FCC. Actually, that's not anything in there. Yeah, there's nothing essentially in there. That's just a geometric one. FCC plus this phase going to another phase. So that right here, that's a peritectoid. You may consider this to be a eutectic here and a eutectic here, but I might not expect you all to kind of see that just because it's very hard to see. Or it's very, 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 very small. Excellent. Let's look at 0.5 TA at 1100. So let's go ahead and maybe put it right around here. Excellent. So let's draw our isotherm line. So what phases are we in this region? So we are, I'm going to call like P1 is equal to FCC, and P2, I'm going to make it Fe2TA. So we're right here. So what are the components in this system? The components are Fe and Ta. Excellent. What phases exist, name explicitly. Composition and fraction, and what chemical potentials, what are the degrees of freedom? So let's just do the degrees of freedom right now, because my degrees of freedom plus phases equals C plus 1. Components are 2, it's these two. Phases are 2, so our degrees of freedom is 1. Excellent. The composition in phase 1, or FCC, is going to be way over here. I'm going to call that like 0.03. Composition in phase 2 is going to be equal to, let's call that basically 0.6. So if I want the fraction in phase 1, it's going to be equal to, in the denominator, it's just going to be 0.6 minus 0.03. And now what I'm going to do, again, if I want phase 1 over here, I'm going to run the opposite. So it's going to be 0.6 minus 0.5. And fraction in phase 2 is going to be equal to, denominators is still the same. And now it's going to be 0.5 minus 0.03. Makes sense because we're closer to here. We should be larger in this phase. We got it. And if we are in two-phase system, that means our chemical potential of phase 1 must be equal to chemical potential of phase 2. We've got it. Excellent. Let's go ahead and take it out here. All right. So we did this, we did this, we did this, we did this. Now we're asked to basically draw the free energy curves at 1600 C. So let's go ahead, let's zoom in a bit. I'm going to draw the line here. And what we're going to do is we're going to actually go a little bit up. And I'm going to go black, and I'm going to go ahead and say here and here. And what I'm going to do is every time, again, like we've done before, I'm going to just draw these little regions here. Every time we cross a line. And then finally right here. So let's go ahead and list it out. So right here, we're liquid. Here, we're liquid plus phase 1. I'm going to call this, this is going to be my P1. Then we're pure P1, right? And then I'm going to call this P2, and this is P3. So in here, we are P1 plus P2. Then we're pure P2. Then we're P2 plus P3, and then we're P3. Now, I'm going to give each of these some different colors. And then we know, but actually before we do that, I'm going to actually put my common tangents in black. So here, whenever there's a two-phase region, I need a common tangent. So I'm just going to do it like that. So first phase is liquid. So I'm just hanging out here. I'm going to touch this, and then I'm going to escape because it's never going to come back again. I'm going to call this P1, my solid. So I'm above here because, again, I'm the lowest free energy wins. Now we're in a two-phase region, so common tangents must touch. They must be equal to one another. And then, so I have P1. Now I'm just hanging out here as P1, but then I'm also P1 plus P2. So I need to hit here, and then I need to go away. I'm going to call this P2. P2 is just high over here. We're a single phase region, but now we're P1 plus P2, and then we're just P2. And then actually I'm missing, I must have written over it. Here's another common tangent right there. So let's go here, and I need to touch. See, it disappeared. What happened? What happened? There we go. So now I'm going to touch this, and then I'm going to disappear. And then finally, let's do another one last color, orange. I'm going to call this P3. So now I'm going to go over here, touch, and then just hang out. And there we go. Those are your free energy curves. Yeah, again, mathematically, my chemical potential, remember, is just change in Gibbs, number of particles, temperature, and pressure. That's equivalent to the slope. That's why we have the common tangent. And we'll see you all in the next video. Thanks. Bye.